Hello, and welcome to this Richardson RFPD and Qualcomm webinar. With us today is Cliff Zetz. Cliff is the product marketing manager of SAW and LTCC products at Qualcomm. So Cliff, go right ahead.
Good morning, everyone. And those of you that are in Europe, maybe good afternoon. I welcome you to today's webinar. As Katie mentioned, I'm with Qualcomm. Recently, let's say, joint venture slash acquisition by Qualcomm of the Epcos SAW BAW LTCC business. So very happy to be with you today. I'm very happy to be with Qualcomm as well. And I'm going to go through a presentation that, obviously with the limited amount of time, we can't get into too many details, but we're going to discuss let's call it the filter solutions for IoT, and everybody calls everything IoT, so I'll get into that a little bit, and with a pretty good focus on Wi-Fi, in particular Wi-Fi 6 and 6E, where we're pushing a lot of development effort into developing coexistence filters, which are highly required and in high demand. So we'll go through that, and questions, I guess, will be at the end. If there's some pressing question that you have to have an answer while I'm doing it, I have no problem, in answering that, in between. But we'll try to keep them to the end, and we'll move forward now. So, as I mentioned, by the way, I'm based in New Jersey, in the Qualcomm Bridgewater, New Jersey office. Of course, the headquarters for Qualcomm is San Diego, and the headquarters for the SAW and BAW division, if you will, or acoustic filter division, RFFE, BU business unit, is still in Munich, Germany. We have factories, they'll briefly just a quick overview. We have factories in, Munich is R&D. We have front end factory there as well. We have Singapore for back end and front end, and we have Wuxi, China, also front end and back end. So we have quite a global footprint. We have design centers in San Diego, of course, in Munich, Germany, of course, Singapore, China, as well as Orlando, or pretty close to Orlando, Florida. Quickly, the portfolio of the RFP60 division of Qualcomm. We have, of course, a huge focus in the cellular phone, mobile phone arena, as well as let's call them the modems that go into PCs and so on, the radios. A large portfolio of duplexers, multiplexers, and of course discrete filters, from band 0 to now band, 70, at least 79 we're up to with 5G. So we have combinations 2-in-1s, 3-in-1s, with a bunch of diplexers, triplexers, and so on. Also, to support the cellular arena, cellular market space, we also, it's not listed here, because it's not necessarily an acoustic part, but has acoustics on it, are, of course, our front-end modules, what we call POMIDs, PA modules, as well as BENIDs, which are the receive modules for cell phones and the such. We're not going to discuss those today. That's another hour or more. But like I said, we're going to mainly focus on Wi-Fi, so that's the next sector down there, connectivity, what we call connectivity. And the other thing I'm not going to discuss today, again, another hour discussion, would be what we call very front end, which is GNSS, GPS, which we have a huge lineup of components there. If there's any interest there, make it a question at the end. Richardson and myself will address it, later in a separate conversation. Okay, let's make sure this thing is clicking through here. Yes, okay. That was my user error there. Okay, so just an overview. Sorry for the small print, but basically it's just trying to give an overview of, the pictures, of course, are the markets that we serve, the applications that we serve. And today's focus will be this little guy up here, access points, for example, a little bit more in the smart home and home comfort, a little bit about smart meters and so on. Not so much in the consumer electronics wearables. That's, again, another conversation. So our acoustic lineup, just to skip through here, we have filters from 300 megahertz or so, even a little lower, to now 7 gigahertz for the Wi-Fi 6E. And also, again, we won't cover it today, also in the UWB area, which is up to even 8 gigahertz. So we are covering that entire spectrum and in between. We have, of course, we have to do narrow, ultra narrow, and very wide. In the Wi-Fi area, it's very wide. In the IoT sub-gigahertz space, we have some ultra narrow applications. In Europe, it's 2 megahertz wide, at a gigahertz, so that's pretty narrow. And we have some technologies to take care of that. And we have components that go up to operate in environments of up to 125 degrees. It's called automotive environments, on the roof of a car, for example, a GPS antenna on top of the car. Gets pretty hot out there in the Arizona desert, and all the components have to withstand that type of environment. I won't go through the rest. Let's go to the next. Some of the more important things is, how do we do this? And we do it with our technology. So we have the chip. It's called the chip technology, which we'll talk about now, packaging technology, and then, of course, module technology. So we have, from A to Z. So for the process or chip technology, let's call it, we have, of course, the old standby SAW, surface acoustic wave. That's still our mainstay, and still a lot of what we do, of course, is based on the basic technologies and physics of SAW. And we still ship more of those than the combination of all the other three, for example, that are on there. So the SAW, we have done some pretty cool things to bring the capabilities up to. We say it's right around 2.7 gigahertz, even though there's nothing over the 2.4 Wi-Fi at the moment in between. In fact, we even have some parts, SAW filter parts at the CBRS 3.5 gigahertz, which we're working on. So we can stretch the SAW technology pretty far to the right there on the curve. And then we also push the technology in terms of performance, very high performance over temperature, like I said, the very narrow bandwidth and things we need some technology. So we have, for example, TC SAW, which is temperature compensated SAW. So we add a layer of, let's call it, I don't want to get too detailed, but we add a layer of physics to the filter. And that basically what it does is it stabilizes the temperature drift. So the SAW plot curve performance tries to shift, and this compensation layer basically compensates for it. Just to be a little repetitive on the word. I show you a little chart on that a little bit later. In the middle is our ultra SAW, and that is very unique technology, which provides for, again, I can't talk to it, it's almost like a semiconductor process, and that provides for performance, again, at the 2.7 gigahertz range, and in fact, at the 2.4 gigahertz Wi-Fi, not so much for Bluetooth, but for Wi-Fi where you really need it, high power capability or power handling capability, rejection as good as BAW, in some cases even better, and insertion loss very, very good, very, very good. So at 2.4, most of our new developments are in the ultra SAW, freeing us up, if you will, the BAW, which is to your right, for our demanding coexistence BAW development for Wi-Fi 6E. So what I mean by coexistence, I'll get into that a lot, because that's really a hot topic, in the market. And you need to have coexistence LTE. So your LTE bands 4G, let's say, 7, 40, 41, 38 even. as well as coexistence between the 5 gigahertz Wi-Fi and the 6 gigahertz Wi-Fi. So those are all very important, and we are working on a number of parts that provide that. So even Wi-Fi, you have to worry about your coexistence with 5G now. So 5G is becoming very popular. I read every day how many millions and tens of millions of phones that are being sold with 5G capabilities, and infrastructure is going out there like crazy. So you have a coexistence issue with your Wi-Fi hotspot in your house, for example, or hotspots on campus at your college or what have you. So that is our technology, our process technology. Just not to bore you with too many curves, but you're going to see a few of these. This is an ultra SAW versus SAW. So you can see the SAW filter, the red, very good. But the ultra SAW, you can see, is a much tighter skirt on both sides. So we offer, let's say channel, we can do channel 1 through channel 11 band edge, for example, with this technology, as well as we can do it, of course, with BAW as well. If you're looking for channel 1 through 13 Wi-Fi, the red is perfectly good enough, and the performance is still very good, but you don't get necessarily the band edge. So we use it where we need it. So the BA96 A has a part number called the BA7539, just for your benefit there. And similar comparison chart, BAW, bulk acoustic wave versus SAW. And you can see the red is, of course, the BAW, and very tight skirts, exactly what you need in your whatever channel 1 through 11 or channel 1 through 13, whatever the case may be, very tight, high rejection of the adjacent bands. It's always good to see it in the picture rather than just to talk about it. So that's the front end. Sorry about that. That's the front end. Now the back end, or the packaging, and we have a wide range of packages. Everything from ceramic. In this case, it's a ceramic. It's a 3x3 millimeter. That's our mainstay, and that offers hermetic seal. As I mentioned before, temperatures up to 125 degrees, and as far as that type of environment. And this just shows you how it's built. Very harsh environments, automotive and outside applications, smart meters that are outside, and so on. So a lot of sub-gigahertz or sub-1 gigahertz parts, we still use the 3x3 millimeter. However, the CSSP to the right, whether it be 3 copper frame is actually equal to, for the most part, the ceramic package shown to the left. And the one in the middle is more of our consumer package. It doesn't have a copper lead frame. It's more of, let's say, the industry we call a glob top. And that's, again, for consumer applications up to 85 degrees C, so minus 40 or minus 30 to plus 85, for example. Not a lot of humidity necessarily in the environment, et cetera. Looks kind of a crazy little chart here, but this just kind of gives you an overview of all the different types of filter architectures, if you will, from the old standardized single filter, so one antenna in and antenna signal in and output one to one, and that's of course still the most common. Diplexers, as I mentioned, we have a number of those for GPS. We have a number of those for sub-gigahertz. We have a number of those so very diplexer, of course, is very popular in Wi-Fi, where you have a 2.4 to 5 gigahertz system. So you want to, cut back on the number of antennas, because the antennas are expensive, take up room, and so on. So you can use one antenna and diplex via an acoustic filter structure, separating the 2.4 and the, let's say, the 5 gigahertz as an example. 2-in-1 filters, so you have the same 2.4 and 5, and you don't mind using 2 antennas because you want to optimize performance. So you could put, in essence, you have a 2.4 and a 5. We don't necessarily do that one yet, although we do actually have that. Not a high demand for such a thing. That's used more in GPS, I would say, where you have two different GPS frequencies that you want to have a separate signal for. Or another popular one, for example, would be a sub-gigahertz, let's say a LoRa type of application for 915, along with Wi-Fi at 2.4. We have that as well. Triplexers, duplexers are primarily used in the cellular world. Quadplexers, of course, 4, and so on. I won't go through them all. Not the essence of this presentation. Another look at SAW versus BAW, and this is the B7520 versus the BAW B8857. So you could see, very specific differences, wideband and the wideband and the narrowband. I don't know if you can see my pointer or not, but that's what it looks like. And BAW is certainly better than a standard SAW, but the TS SAW would pretty much look the same as the red BAW signal there. I'm sorry, in this case, the blue BAW signal there. It just depends what you need. BAW has some advantages as well. So, we obviously are in competition with other acoustic filter suppliers, but also, let's say, the competition for the socket, for you, can we use a SAW? Or can we use an LC filter? Can we just use a basic LC network? Maybe we can get away with a ceramic multi-layer LTCC filter, which certainly are less expensive than an acoustic filter, and that's fine if the application calls for that and enough to meet FCC or whatever you're trying to do. All good. Obviously, the lower cost filter is a good way to go. But when you get into coexistence issues, different radios working together, and you need close-in or you need close-in rejection or attenuation, and better out-of-band rejection, harmonics, for example, then an acoustic filter is a better choice. And obviously a little higher cost. It's a process of a chip, as I showed you, and a back-end package versus the LTCC type of filter, which is pretty much done all in one run, and materials and so on. But again, it's just a question of what you need for your performance, what criteria you have. And nowadays, lots of coexistence issues exist, and big demand for acoustic filters. And we have some low-cost, I'll show you some low-cost acoustic filters to provide a good alternative with a small premium versus the ceramics. So I'll get into the IoT / what I would call sub-gigahertz. Like I said, there's lots of ways of looking at IoT. There's Wi-Fi IoT as well. So I don't want to get into all the semantics, but let's just I'm going to use for today's presentation, IoT is sub-gigahertz. This is just a copy of what we would call a product guide or fighting guide, outlining all the different types of IoT filters we have for what we call industrial applications. And so I talked about the packages, sizes, so 3.0 by 3.0, 1.4 by 1.1, 1.1 by 0.09, and for the higher frequencies, the 2.4 or 5 gigahertz, we actually have 0.09 by 0.07, 0907. So really getting small for those compact applications. But for industrial, the 3 by 3 is still very popular, has, like I said before, the highest environmental robustness of all the different packages. That's an example of a smart meter, by the way. So, besides coexistence, I'll kind of go back a little bit here and go back to the more historical issues of filtering. Coexistence is a little bit more, a little more newer, if you will, or more modern issue because of all the different radios. But the old stuff, the old problems still exist. Noise. And this is a funny story. That is a picture. That's the display of our analyzer in Munich, and our applications engineer basically had an idea. Let me just put this analyzer on the windowsill. If you've ever been to Munich, it's pretty noisy from a real noise point of view. So he wanted to see how noisy it is in terms of RF. And that's it. I mean, you see all the different frequencies all working together. So you have people opening their car doors with their RKE, keyless entry. There's Wi-Fi in the building. There's Wi-Fi down below in the coffee shop, for example. It's called Red Coffee. Great coffee, by the way, in downtown Munich. They have their Wi-Fi, and then there's Bluetooth printers. And so it's all kind of appearing and working at it. So you're working and you see your noise floor is just getting higher and higher. So the solution, at least in our mind anyway, is of course the SAW filter. Again, because of the, mainly because of the coexistence and also harmonics. So you know, if you're a sub-gigahertz part, your second harmonic, let's say 915 plus, or actually in Europe it's 865 times 2, 1.6 to 1.7 gigahertz. You want to make sure your second and third harmonics are covered, and an acoustic filter will do that much better than alternatives, let's say. I mentioned all the different types of the bandwidths, and this is just an overlay of 3 different parts, from ultra narrowband in black to the more wideband in blue. It depends what you want, and there's obviously there's trade-offs. The wider bandwidth, the insertion loss is a little worse. Narrowband, typically the insertion loss is a little better, but it also depends on the rejection that you need, and it's all different trade-offs. So there's no one formula, no one statement you can make. It just, we always say it depends. It depends on what you can live with, and you only need one side, say the left side, where in the world of sub-gigahertz band, I want to say it's band 20. I always forget that, actually band 20, or there's also a band 8 that is very close to the IoT, say 900 megahertz. Just kind of cut it in the middle there. So you need a very good left skirt, or left side rejection, and the right side not so much concern. So we have filters like that as well. All different. Oops, hello? Oh, okay. I had another call coming in, sorry. Okay, now I mentioned TC SAW, so temperature compensation. I just wanted to show you, you can't mention something and tease everybody without giving some more information. So this is one of our standard 3x3 millimeter saws, B3716 without TC SAW. So you see the different curves, black, blue, and red. Hope you can see the colors. And you can see the shift over the various temperatures. So not optimum if you really need that center frequency to be lock solid, and you want to use the edges of the bandwidth. And again, this is a very small bandwidth. You see 2 megahertz. The same 2 megahertz requirement, same part in TC SAW, what we call B3440, and you can see all over each temperature, it doesn't move. It's the same. So the compensation layer locks in, and very reliable in terms of temperature. And there's a lot of applications that are used, in minus 40 to plus 85, plus 105 applications, and you want the performance to be the same. And that's what this does for us. So now I'll get into the coexistence issues. Again, definitely a hot topic. This is just a look at the spectrum, frequency spectrum, which I see got a little messed up there with my little red, but the red and the white should be moved to the left. So from band 40, so that's this is the 4G coexistence issues here. So band 40, Wi-Fi in the middle at 2.4. To the right side, band 7 is primarily Europe, and band 41. So with the recent combination of Sprint and T-Mobile in the United States, for example, band 40 and band 41 are in high use in cell phones and even IoT applications. And of course, you have Wi-Fi and Bluetooth right smack in the middle of that. So you need to, let's say, protect against each other. And moving to the right, now it's more of a 5G issue. But by the way, these band 41s and band 40s and band 7s are also, let's call it, reused in 5G. So it doesn't go away at 5G if you have a 5G phone. Of course, most 5G phones for the next X number of years will be using the 4G capabilities as well, right? You always have that as a backup to the infrastructure. But even if it's just a straight 5G, you still have use of those bands, those 4G bands, if you will, the band with the B, and then in 5G it would be called N40, N7, N41, and so on. And at the, strictly, let's say at the 5G level, the concern, of course, is N79, which is right on top of your 5 gigahertz at 4.4 to 5, and of course the 5 gigahertz, which I lost again here. Sorry about that. Starts at, your first channel starts at 5.15, so you're very close to each other, and 5 gigahertz is very close to 6 gigahertz. So that's the coexistence scale. I guess that kind of got messed up when I sent it over, but that's okay. And so I'm not going to go through all the literature here, but I just explained interference, of course, is key, and you need to mitigate that. You need one of the main issues, of course, is the power from your LTE or 4G is going to leak into your receiver and totally obviously mess up that received signal. So you need a filter, in short. So this is a really good look at all of them together. So your LTE bands here to the right and to the left, band 7, band 40, 41, and so on, and your Wi-Fi channels 1 through 11, 1 through 12, 1 through 14, whatever the case may be, you can see are in there, and these guys are right on top. And you need a good 2.4 gigahertz filter to provide the coexistence there. And we have a number of them, not just one. We have a number of those. We did some comparisons of SAW filters at 2.4 gigahertz. So I think these are two of the more popular parts, B7506 and 7520 versus LC. And obviously, no challenge there whatsoever in terms of performance. Again, it depends. If LC is good enough, then yeah, that's super cheap and you go with it. But again, in most cases where you're worried about your band 40/N40s and so on, you need an acoustic filter. In our case, I would say SAW filter is your best approach. And similarly, I don't know why these things got messed up, but this is versus ceramic filter. It looks very much the same. And we also have some diplexers. This AB53 is one that's in development. It's basically going to be released for production very shortly. And you can see the 2.4 signals are here. So the diplexer is in blue, the acoustic diplexer. So the way we build our diplexer is we actually integrate a SAW filter into let's call it a module, with 5 gigahertz functionality being provided by an LC type of network, and that would be this blue signal here. So you got an excellent coexistence 2.4, and have a diplexer. And if this 5 gigahertz signal or passband is good enough, wonderful. If you need an additional filtering, depending on what your application is, then you could add another 5 gigahertz filter, whether it be a PCC type or an acoustic type, which I'll show you in a moment. And this is a similar part. This is a 2.4 with a 5 to 7 gigahertz diplexer. So for Wi-Fi 6E applications, similar SAW filter on the input for the 2.4. And your 5 gigahertz here, for example, in blue, very low insertion loss, very similar in the passband to the LTCC diplexer. But again, the bonus, of course, is you get the 2.4 gigahertz filter into one component. So it's an integrated device. At at 5 gigahertz. So for Wi-Fi 6, let's say Wi-Fi 5, Wi-Fi 6, and I'll get into Wi-Fi 6E in a moment, but even Wi-Fi 6E, the concern, at least from a cellular phone perspective, of course, is your N79, but you also have your N77 and N78. That's the little integrated box here. Right on top, your N79 is right on top of your left skirt of your 5G or 5.15 Wi-Fi signal, Wi-Fi 5 gigahertz signal. And you, again, more and more co-location, coexistence issues are coming up, whether it be in hotspots or certainly in phones, it's an issue. You know, your phones have more electronics and more radios in it than anything. So obviously we have filters to mitigate that for cell phones, which we also use similar filters for access points and IoT applications and smart speakers and so on. So these are real plots, based on performance of these parts. So this is the B7540, which is our first 5 gigahertz Wi-Fi filter, if you will, and looks really great. It's in a small 1109 size package and very, very good performance, as you can see. It's primarily designed for Wi-Fi 5 and Wi-Fi 6, not so much for Wi-Fi 6E, because at Wi-Fi 6E you need you need a different coexistence there. So you need coexistence at this point. So this hump has to be a little lower. It has to be down to the 50 dB range for Wi-Fi 6E coexistence, just as an example. And that is similar. It's just a different part, just to show that we did our homework here and looked at it over various different use cases. Similar deal. And now our offering of Wi-Fi filters. So we're just going back for our offering of what's called IoT filters. We have product guides. We have most of them are on the internet, and we have product listings of those. So if you're interested in that whole list, of course, we will provide that. Because most of them are we have hundreds of them in production. Wi-Fi is a little different. It's a new developments going on here. So I'm going to show you a little bit more on the part numbers that you will have data available as well upon request to Richardson. So our focus is not only, but our focus is certainly on Wi-Fi 6 and 6E. That's the highest growth in the market right now. In particular, Wi-Fi 6E is ramping up. Many of the access point companies, OEMs, are working feverishly to get their Wi-Fi 6E systems out the door while they continue to ship Wi-Fi 6. So if you go to your local retail store, mainly what's on the shelves now, you have Wi-Fi 5s and a lot of Wi-Fi 6s from all the big names, from A, as in Amazon, to Z, really. There's many companies. And like I said, mostly Wi-Fi 6, different performance levels, depending on how many radios, their MIMO scheme, multi-user MIMO scheme, and so on. There's a lot of different factors. So you have to do your homework and, get the access point that you need. And now there's also extenders. So as everybody knows, the Wi-Fi is being stressed, as people are going back to work now, but for the last year and a half, a lot of stress on your Wi-Fi with yourself, your wife, or spouse, let's say, plus your kids, all working from home and from your office to the pool, basically. So lots of bandwidth required, and Wi-Fi 6 has been pushed along because of that. The pandemic has really pushed the Wi-Fi 6E adoption and the design, and that is being done as we speak. So just some numbers, ABI Research estimates 1.4 billion Wi-Fi chipsets, Wi-Fi 6E chipsets by 2025. To be honest, I think that'll be a higher number the way it's going now, but I'm not a market researcher, so can't really say. Again, it's still designs at Wi-Fi 6, mesh tri-band networks. a little tighter from a coexistence point of view because of Uni 4 that FCC has released recently, and I'll show you that in a moment. Really stretching the technology of acoustic filtering to keep the coexistence between 5 gigahertz with Uni 4, as you see here, to the first channel of the Wi-Fi, the 6 gigahertz for Wi-Fi, which starts at Uni 5, for example. I won't go through the market numbers, but like I said, many are shipping, and many with 6 gigahertz are being prepared to ship and already shipping in many cases. So, bottom line is acoustic filters are definitely required to tackle this not just coexistence, but multi-coexistence issues, including the 5G, as I mentioned earlier. Soon to a theater near you will be Wi-Fi 7 already. It's kind of crazy. These Wi-Fi protocols are moving as fast as cell phones now. The time it used to be 10 years between Wi-Fi modulation schemes, let's say 802.11 XXXX. Now it's 3 years. It used to be 10. I can show you. I have a chart. I believe in the next chart as an example. Starting at Wi-Fi 4, 2009. Wi-Fi 5 wasn't until 4 years later, 2013. Then there was a big gap between 5 and 6, 2021. And then 2021 also is going to roll out the 6E. Wi-Fi 6 was already back in, to be honest, probably 2019. 2018, 2019 was the Wi-Fi 6, so it was 5 years. And then, 3 years later, 2 to 3 years later, you have the Wi-Fi 6E. And 3 years later, we have the Wi-Fi 7. These are different codes. So just a brief history on that. So we all know 802.11 N and so on and so forth. Wi-Fi 7 is BE, by the way. Then the Wi-Fi Alliance came in and said it's getting too confusing, especially at Wi-Fi 6E. They're both 802, that's 802.11 AX. So that's when, they said, let's think of a good name that everybody can agree on. So real basic Wi-Fi 4, Wi-Fi 5, Wi-Fi 6E for extended 6 gigahertz, and then Wi-Fi 7. But, they're all the same. And then this chart just provides information about the modulation, the MIMO. That's another interesting point, going from, 4x4 maximum. This is maximum MIMO. Isn't necessarily that's what you're going to get. But the average, I can tell you, at Wi-Fi 6E is 4x4, average in the industry. Whether or not it gets to 16 by 16 for Wi-Fi 7, MIMO becomes more complicated because we talk about different streams, 2 gigahertz and maybe 2 by 2, and the 5 gigahertz maybe 4 by 4, and it's all different combinations. So, but these are the maximums. So, as you can imagine, the front end becomes flooded with filter requirements, which is good for us. But it's a challenge for you guys, the designers, to get all the coexistence issues resolved and keep the cost, obviously, and size of the board down. So our filters we always try to develop to the small side, so they're it's not all filters, and then there's your SoC radio. We want it to be in line. So that's why I mentioned 1109 size. And up to 1814 is about our biggest filter for Wi-Fi so far. It's a Qualcomm offering, just to kind of give you an idea of at least Qualcomm's offering. We have what's called Networking Pro platform, and we have an immersive home platform. So this is a mixture of, just to give you an idea, Wi-Fi 6. And when you get to the immersive home, it's more Wi-Fi 6E, and with MIMOs of even 8x8. So these are the SoCs that we sell to the access point manufacturers and so on. So we work together with them to define what the filters need to look like to optimize the system. That's I'd like to show this. It's a great look at the spectrum. From 2.4 to 5, and now 6 gigahertz, and you can see very close proximity between, and that's not even including the Uni4, which comes here. And you need lots of coexistence, protection, filtering. And you can see that, this is more for the software side, the number of channels available. But, the key is, the length or width of the channels. So at 2.4, they were 20 megahertz, maybe 40. Going to Wi-Fi 7, they're going to be 320 megahertz wide. These are 160, the Wi-Fi 6E. And what's not even shown is the 320, which would be primarily in the 6 gigahertz area, but also, instead of 160, it'll be twice that. So again, the filtering becomes ridiculously challenged, let's say, challenging. This is what I was talking about, the Uni4. So this is Uni 1 through 3, and this is your 6 gigahertz Uni 5 through 8. And recently the FCC approved, and it seems to be happening in other countries as well, the use of a piece of the old V2X, not the old, still exists, V2X spectrum, which is coming, very slow to adopt, but it's definitely coming, and cars will be talking to cars. It's a very good safety feature, but they determined that V2X doesn't need all that spectrum. They could do it with this little piece here, especially moving to 5G cellular. So everybody's happy, and the Wi-Fi guys, let's say the Wi-Fi world, got this extra spectrum, and what it does is it enables the use of the channels to go from, or to let's say to increase the channels from 80 megahertz channels to 160 megahertz just by getting this, because without this you're only able to use the 80 because it's chopped off here. So this allows an extra 160 megahertz channel, and then of course going to 6 gigahertz as well. So very important, very, very important legislation. So here's some marketing stuff, just to get off the technical stuff for a moment. So this is our target markets from the Qualcomm RFFE, RF360 perspective. So we cover, everything. Again, we cover more, but again, go back to our focus: Wi-Fi, Wi-Fi 5, 6, which is primarily smart home, and then of course Wi-Fi 6E, which was pretty much just networking, but now it's also reaching into audio and other types of applications. And certainly automotive cars are already at Wi-Fi 6, and there's already cars being designed with Wi-Fi 6E. Why we need it, I don't know, but that's the way of the world. Your cars are clearly a rolling computer with lots of Wi-Fi capabilities. So you could drive forever and not have your kids saying, "Are we there yet?" Because they're totally busy watching their movies and so on. So I guess it's a good thing at the end. And these are our part numbers that would go into, again, more details, data sheets and so on are available later on. It's a little small, sorry about that. These are, it's a better view of our focused 2.4 gigahertz filters. So SAW and BAW, as I mentioned. So SAW includes our ultra SAW with the details, low insertion loss for some focus more on the band edge. It just depends on, again, the application, but we have a broad offering. There's not a filter that fits all, that's for sure. We need many of them, many different types, I should say. And this is our 5 gigahertz, this is our roadmap, if you will, to develop the filters. It looks a little strange, I guess, maybe, but these are the pass bands for which we need filters. So this is a 2 by 5 gigahertz radio application, which is still very popular at Wi-Fi 6, provides simultaneous radio applications, low band and high band, if you will. And then the Uni 1 through Uni 3, the Uni 1 through Uni 4, different filters to provide the coexistence with the 6 gigahertz over here. Europe has a little different look. We're not sure. It's still up in the air. If anybody in the audience knows the latest, I'd be happy to listen to you. We've heard different things, but right now it seems to be cut off at the 6425 on the Uni-5 because of other radios, government primarily, radar, and so on, in the Uni-6 spectrum in particular. But there's some thought about breaking Uni-5 and then Uni-7 and 8 and not using 6 as the transition uniband, if you will. So we shall see. We don't have any control of that. We just react and try to stay on top of it. And we'll even do filters, in thought of, or in anticipation of legislation being passed. Sometimes we win, sometimes we lose, but we always try to stay ahead and be on time for when that happens. So I'm just going to flip through. These are what we call our little sparkle sheets, but we have full data plots and everything, which I had to take out for NDA reasons. But anyway, so we have our 6.5 gigahertz part, our 6 gigahertz filter, the Uni 1 to Uni 4 filter, Uni 1 to 2A. So this is the split band coming up, the 1 to 2A, and then the 2C through 4. So we actually cover the Uni 4 band and it's called the half band filters. Let's say our low cost, really just more for the 5G coexistence, lower cost BAW filter, and very small, 1109 size. And our coexistence filter. So the other one is more the standard filter, the one I just showed you, the AS80. And this guy is the coexistence filter with Uni 1 to Uni 3. That's the diplexer I talked about earlier. Just to give you an idea, it's separating the two curves, the 2.4 and the 5. Typical block diagram, and everything in blue, and now actually the green is now blue. That was in development. So we cover all these bases, all this front end, all this filtering, and we actually are in the process. We actually have a few already getting ready for the market on front end modules. So switch, PA, and LNA. We are selective there, what we're doing. But if you want to talk about that, I'm open to that. And we may have something you need already, or we may be in development of something, or it may be a great idea that we should be developing that. So we're very open to that. We do have capabilities at PA, designing PAs and LNAs. And of course, the module, as I mentioned, cellular phone, we're one of the leaders in front-end modules. So we definitely know how to do that. We have a lot of competence there. And we have good competence in PA design, so we're getting, we're definitely ramping that. Just a matter of resources and focus with filters, because this is a big burning issue in the market for good coexistence filters at Wi-Fi 6E. And we said, let's put our resources on that and solve some problems for the customers, and then we can always go back. And that is it. I hope I'm okay on time, Katie.
Yes, great. Cliff, you did a great job. We're good on time. We are going to move into some live Q&A right now. So, Cliff, I'm going to start off with this one here. Will coexistence be a concern with Wi-Fi 6 and 6E?
Okay, thank you. Yes, so I just covered that a couple minutes ago. One of the last slides. So, yes, it is the biggest concern, I would say, from a front-end point of view. So that's, like I mentioned, we are developing and already have samples of 5 and 6 gigahertz filters for the 6E spectrum. Yes, big concern.
Okay, Cliff, thank you for that answer. Another question here from an attendee. Is it possible to reach for smaller passband using BAW or SAW technologies? For instance, 20 megahertz for GNSS bands.
Okay, so let me just make sure I understand. So a 28 megahertz bandwidth for a GNSS filter is the way I interpret that. Yes, that is possible. That is possible in SAW filter technology, actually.
Okay, great, Cliff. Thank you so much for that answer. We've got another attendee question here. It says, I wonder if there is an ultra-low consumption energy transmitter. I'm working with designs and energy harvesters modulos. Thank you.
Oh boy, ultra. That seems to be. Let me read that here. Hold on one second. This one here. I wonder if there's a ultra-low consumption energy transmitters. I don't know. Not my field of expertise, sorry.
All right, thank you, Cliff. No worries. We're going to move on to the next one. Can you go back and review the products that Qualcomm offers to mitigate LTE coexistence in Wi-Fi and Bluetooth 2.4 gigahertz systems?
Yes. Okay. Let me go back to the magic screens here. So here, one second. Here we are. So, in other words, this one, I think that was the start of it, if you will. So this shows the 4G coexistence problems, let's say, with Wi-Fi and Bluetooth, because Wi-Fi and Bluetooth are in the same frequency spectrum. And then we have the filters, this way. For example, SAW filters, just to give you a quick example. The two filters, so let's just use the 7520 in red. As you can see, that provides the perfect bandwidth, passband for the Wi-Fi, while rejecting the LTE signals to the left side and to the right side. I hope that covers the question. And we have a number of those filters. These are not the only ones. Just so we have different variations of those. And these filters, by the way, it's another good point to brought the question up, actually are really easy to design with. We've integrated the matching, so you don't need any external matching. So you just, all you have to do is go through your S parameters, get it designed in, figure out where it needs to be on the board, and so on and so forth, and you don't need to do any matching or tuning.
Okay, thank you so much, Cliff. The next one here, what frequency and what RF concerns come with the Halo system?
Yeah, I didn't talk about Halo too much there, but Halo, I'm not sure if it's ever, I can't say it's ever going to be widespread. There is a lot of work being done there. It's 802.11ah, H for Halo. That's some gigahertz, so 915 megahertz center frequency, using the 902 to 928 in the U.S. and Europe, the similar European bands, 866, say, center frequency. Same concerns as standard IoT, your LTE bands, at the sub-gigahertz level. So there's LTE bands in the 800 and let's say 864, I believe it is, in the U.S., for example, and so on. So yeah, same concerns. We have filters that will play with Halo.
Okay, great. Thank you for that answer. Next one. What are the package sizes available from Qualcomm?
Yeah, okay, so I briefly went through them. So just to review, starting as small as 0907 or 0.09 millimeters by 0.07 millimeters. And I won't go through, I won't say the millimeter word again. So to 1109 or 1.1 by 0.09, 1.4 by 1.1. We have some in the ranges of 2 by 2.5 and 1.8 by 1.4 in between, up to 3.0 by 3.0. And the multiplexer packages and things are a little different, but for discrete filters, those are our package sizes.
Okay, great. Thank you so much. So last question today, Cliff. What is UltraSaw?
Without providing too much details, UltraSaw is a brand name, if you will, for our new technology that's called TF-SAW. And it's a new type of SAW technology that's similar, based on a semiconductor type of process. And that's pretty much all I could say about it.
Okay, great. Thank you so much for that last answer. I wanted to say a huge thank you to Cliff for presenting such great material and staying to answer a few of the attendees' questions. So Cliff, thank you so much.
You're welcome. And thank you, everyone, for attending. I hope you come away with some good information that will help you with your designs. Any questions that come up, as Katie said, feel free to get back to us, Richardson included in particular, who's our partner, one of our disty partners in the field, and very technical and a great help to us. So step up and step out and reach out to any of us.